And because now we're thinking about the electric field, okay, you need to divide by epsilon naught, because how do you turn the, if you turn the electric field to the, it will be this, right? 1/2 epsilon naught, the E field squared integrated over the volume, something like that. Okay. So you just reverse this process, and roughly you can remember this back quite easily. Okay. So and then there's this. You extract out this AK factor, which later we're going to turn into the operator. Right? And then you attach the spatial dependence, which we assume over here to be plane wave. Okay, K dot R naught minus R. Okay. And of course, there's the complex conjugate part of this. Okay. So now to quantize this, we just simply turn the expansion coefficient this into an operator. Okay. And then the complex conjugate becomes the Hermitian. Basically turning this into the dagger. Okay, so that's the electric field operator. Right? Okay, so now we basically plug this electric field operator into this dipole coupling Hamiltonian we've written here. And really only the only thing that gets coupled to it is the R dot E part. So let me write that down. I'm going to call the interaction part, which describes the dipole by the H interaction. This is equal to minus E plus R dot E. So now we go ahead and quantize this by plugging this into here. And let me be specific. We're going to only consider an atom with two levels, two adjacent levels. And why is that okay? So once again, I need to explain something about when do we actually use this kind of Hamiltonian. We're going to consider an atom with just two levels. And I'm going to call the upper level the excited state and the lower level the ground state. The ground state is not actually the ground state of the atom, but just the lowest energy state that's relevant in whatever experiment you're doing. And there's some transition frequency, which I'm going to call it H1 omega naught. Okay? And then, so with this, I can quantize the atom by, not really quantizing it, I basically just turn this R operator and represent it onto these two relevant atomic states. Okay. So how do I do that? We're going to use the matrix formalism. Okay. So I can turn some operator by expanding it onto a basis like this. E, E, right? And then let's say this is the R term, right? I attach this to the E, R. This is one term, okay? And then adding the ground state. And then remember this is just how you represent a operator onto the using its matrix elements. Okay. And now I'm going to tell you something, is that these states are of definite parity. Okay. What does parity mean? We didn't have enough time to talk about this, but actually this is 0 and this is 0. Basically it tells you that any eigenstate does not have a dipole moment by itself. But there's going to be a dipole moment linking the two, okay? Because this could be an even parity, this could be an odd parity, and if they're adjacent, they must be a different parity. Okay, and then R has parity of 1, so basically that's what happens. But I mean, this part, if you really want to know this, you need to study the hydrogen atom in detail, and then you believe me. Okay. So expand it onto here. Okay, I get that this R operator is equal to E3. And because this dipole is an observable, so its matrix representation should be Hermitian. And for it to be Hermitian, we require that these two be the complex conjugate of each other. And let me just tell you that they're real. Okay? So they're the same thing. Okay? So let me call this something called D, which is the expectation value of the dipole moment. That name is not so bad. Right? And then, because we only have two states, the matrix representation is going to be a 2x2 matrix. Right? So basically, this 2x2 matrix is only going to have off-diagonal elements. So R is represented simply as 0, 1, 1, 0, D. Right? Right. Okay. So now we attach these things. Are there any questions about what I did there? I'm just representing the R explicitly onto a two-level atomic basis.
How do you know D is real value?
I choose it to be real value.
You choose it to be real.
You just throw away a phase factor. Yeah, you can choose it to be real value. So, as I was saying, okay. So now you should recognize this. What is this? Which one is this? Yeah, this is now we don't use X, Y, Z now. We're going to use 1, 2, 3. So this is sigma 1. Right? And I'm going to turn this specifically to this two-level system. I'm going to turn this into a more intuitive form. I'm going to call this is I decompose it into sigma plus and sigma minus. What does plus do? Okay. So the sigma plus, it raises the atomic level. Okay. So when it operates on the ground state, it gives you the excited state. And then this sigma minus, it lowers the atomic state. So it obeys this. Okay. And basically the matrix representation for sigma plus is simply, so this is just this, and this is this. And we've written the matrices so that you know the convention is, if I were to write a state, I expand it onto the excited and ground state with the, so a general state vector would be like this. And this is the, up here is the excited state component, and down here is the ground state component. And this is the convention. And under this convention, we have this being the raising and lowering operator, or the atomic transition operators. Okay, so once I've written that, then I can write this is equal to E times sigma plus sigma minus, right? Okay. So now the interaction of the opinion is minus E, okay. R turns into this, okay, D sigma plus, dotted with E, which now we have turned into an operator. Okay. But writing down the E is very tedious because there are so many factors there. Okay. let's simplify it greatly by grouping some terms together. So over here, really the all that that interaction Hamiltonian is going to care about is the polarization of B, okay? Because this is a vector explicitly, and the polarization is going to be checked by the dipole moment here. Okay. So polarization. This is something specific to the field, and it's just a factor. Okay? Over here, this is the spatial dependence of the field, and it's also just a factor. Okay. So let's group these terms together. Okay. And notice how here's a minus sign. I don't want to carry this around, so I'm going to explicitly define something with a minus sign here to cancel it. So writing down what I was just saying, I'm going to turn this electric field operator into, still we have a summation over the k states. Okay? But then I'm going to group all of them into some factor called G. But G is a vector because we attach the information of the polarization to it. Okay? And it's a function of epsilon k, which is the polarization. Okay. And it's a function of omega k. And it's also a function of R naught. Yeah, basically that's it. Actually, it's also a function of omega, but I don't want to write all that. Okay. So we group all of that into that factor with a minus sign. So explicitly, G is equal to epsilon sub k. Let me label this as k. Times square root of h bar omega k divided by 2 epsilon. I would like to define it with a minus sign. Okay. Defining this with a minus sign gives me a minus sign in front. Okay, which allows me to cancel this minus sign. So I just don't have to carry that minus sign around. Okay. It really isn't that important, this G factor. Okay, and then we can attach this A e to the minus I omega k t plus. Right? Okay. So now when I do this product, operators are going to see the operators, and they have a product in the direct product sense. Right? And these this dipole, which is an ordinary vector, this is going to see this G vector, and they're going to give you some number. Okay. So let me work on the operator part. The operator part obviously is going to consist of this multiplying right? Okay. So if I expanded that, I will have 4 terms. Okay. 4 terms. But now we're going to do the rotating wave approximation, which is to say, well, naturally, these electric field operators have attached to them these phase vectors, and then A dagger has attached to it this one. Okay. What about those dipole transitions? Okay. We're going to think about the so when I expand this, I will have sigma plus k plus sigma minus k then okay, we're going to have 4 terms. Okay. And of course, let's attach the field time dependence to them. There's a e to the minus omega k t here, e to the plus e to the plus. Okay. And then let's think about how these operators evolve in time. So sort of, I'm saying for the free atom, how are they going to evolve in time in the Heisenberg picture? So do you guys remember the difference between the Schrodinger and Heisenberg picture? Okay. In the Heisenberg picture, the time dependence is attached to these operators. Okay. And they are attached how? So let's take this one. Okay. Project onto the ground state and then change it to the excited state. And that's what this raising operator does. Okay, so I attach in the Heisenberg picture, let me just think about the free atom. Because roughly that's still the characteristic time dependence that's going to be attached with these factors. So I get H atom T over H bar e to the minus. This is the thing in the Heisenberg picture. So now when this sees E, it's an eigenstate of the atomic formula. Okay. So this gets maybe En. So this is like E, which is just sigma plus E to the I, E of the excited state minus E of the ground state divided by H bar times T. So and then this thing is just I omega naught T. Right? Okay. So we find that the sigma plus gets attached with it I omega naught T. Okay. Whereas if you do the same thing, sigma minus would have attached a time dependence e to the minus I omega. So this is roughly how they're going. So now let's attach these things into here. Okay. So now that we've written down their time dependence, okay, we can do the rotating wave approximation by saying, well, this term and this term, they are changing at the frequency of omega k plus omega naught. Right? Whereas these two terms are changing with the difference of their frequency. So these two terms are slowly varying, whereas these are very rapidly varying. What happens to terms with rapid variation? If I'm looking at things that's going to happen on time scales, that's approximately equal to that's this time scale, which is saying like 2 pi divided by their difference, then these terms basically disappear. Okay? This is what we said for the rotating wave approximation. But now quantizing the Hamiltonian allows us a better interpretation of what it means by rotating wave. And it tells you what is valid. Okay? So think about this term. Excites the atom, destroys the photon in the field. Right? So this is absorption. Okay. So let me write it. The field comes in with a photon. Okay. This photon excites the atom from the ground to the excited state. Okay. We know that this happens. Right? This is just atomic absorption. So this term is okay. Now this term lowers the atomic state, emits a photon. Right? This is just emission. Right? There's a photon emitted. Okay? This is also okay. But what about these terms? You excite the atom and simultaneously create a photon. This doesn't happen in the usual sense, in the energy conserving sense. Over here, you annihilate the photon while you allow the atom to do a transition downward. This also doesn't conserve energy. Okay. So in a simple setting, we could say that the rotating wave approximation is basically just keeping the energy conserving part, which is these two terms. Right? But let me remind you, this is only valid when you're thinking about the field, omega k, is exactly coupled to omega naught. So that these transitions and these, so that the field is actually causing the atom to transition. Otherwise, this picture does not hold. And this is why the rotating wave approximation is only good when you're doing the exactly resonant case, or the very near resonant case. Completely coupled meaning that omega k is equal to omega naught, or roughly equal to it. Remember when we studied the Fermi golden rule, we found that the transition frequency of the atom, the one that was filtered by the sinc function, the sinc function is not exactly a delta function, right? It had a width. So the transition could happen, it has a zero probability, it has a non-zero probability to make a transition at some frequency band. The sinc function was like this. Okay. And there was a width of the frequency, and this width depended on the characteristic time scale. Okay. And I'm saying here that if we were concerned about things happening at this time scale, 2 pi divided by omega k minus omega, then these things don't need to worry us. In these terms, they oscillate too rapidly and over a long time, this time scale, their action is basically averaged out. That's what we did for the rotating wave approximation when we studied it in, I think, the density matrix part. Okay. Yeah. First, did we talk about this?
We did talk about Fermi's golden rule.
We did talk about Fermi golden rule, but I mean, did we talk about the rotating wave approximation rule?
In a two-level system, we did.
Yeah,
we went to
right.
the density matrix and then we threw up terms in a rapidly varying.
Yeah. So roughly speaking, by quantizing the Hamiltonian, you find that throwing out the rapidly varying terms just tells you that you only keep the energy conserving terms. Because Fermi golden rule and the energy time conserving principle tells you that over a long time scale, energy is conserved. But what happens at extremely short time scale, we don't know. You could have non-energy conserving due to this wave. Okay. So that's the comment I wanted to give. So basically now we turn this, we just keep these terms. Okay.
And you're going to give us a coffee break?
What time is it? Okay, yeah, let's take a break. Yeah, let's take a break.
Okay.
And if you have any questions, you can.